I couldn't do all of this. It was a computer. So that's why you have this very large decimal point. So sorry about that. So you can, I use Excel to generate this table. Okay. We have, so you need the summation squared of the x squared summation, which is given by this. Then for the model 2, so this is our x. So multiply this column by this column in order to get this column for the model 2. So I'm multiplying this x by this y to get this one. Then for this one, we are multiplying this by this. So you're multiplying this by this to get this. So we multiply this by this to get this. Then we are going to, so we have the summation of the x, we have the summation of the y, then we have, that's for the first model, and the summation of the y for the second model. Then we have summation of x, y for the first model. Then we have summation of x, y for the second model. Then we have the summation of x squared for the, because x is just one value. So we already have everything we need to calculate the slope of the line. So we already have everything we need. So using this equation, you just plug in all these values into it. Then we arrived, we got M as this. Then our C, which is the intercept. So we plug in the values because we've already gotten the mean of the X and the mean of the Y. So we arrived at this. So therefore, the line, the straight line that fits the first model is given by this. So for the second model, I'm coming back to this graph. So for the second model, we already have everything we need also. And when you get the slope of the line, we have that this. And when you get the intercept for the second model, you arrive at this. So this is for the first model. This is for the first model. And this is for the second model. So we want to, so we've gotten the straight line for the first model. So once we've already gotten the straight line for the first model. So we got it as, for the first model, this is what we got. So let me just put it here. So we got, let me just make this one x minus, let me reduce the font size to 8. Okay, for the first model, we arrived at this particular line. And then for the second model, we arrived at this particular line. Let me just copy it here. And let me write this as x, so reduce the space. Okay, we got this particular line. So we just want to plot a straight line through it. So we use the value of x1, x2, x3 to get all these values. Then for this particular column, we use these values of x1 through the last x to get these values. So we are going to plot the line now. So this is the line of best fit we got as a result of the model we calculated. While those points, they are actually, this particular blue point is actually a plot of this as a function of this, while the red line is a plot of this as a function of this. So, like I said previously, so for the second model, you're going to plot this particular column. You plot this particular column. the x column. We plot this x column as a function of this one to get the second model. So like I said, the best model, the question is asking us to get the best model that fits the data. So like I said previously, before solving it, I said that the best model is the one in which the slope is close to 1 and the intercept is close to 0. That means that it's really a very perfect fit for the data. So this is the first model, the mathematical model we derived. So look at the look at the look at the line we derived and look at it. Then for the second empirical model, given the values of the line, of the slope and the intercept, we arrived at this particular line. And so like I said, the best line is the one that the slope is close to 1 and the intercept is close to 0, because it shows that the measured value and the calculated values are kind of close. But if you compare the two, you would observe that this particular model, the mathematical model, is actually closer. Even just looking at the values, like the values you have here is kind of close to the values you have here. Then if you look at this one and this one, they the the difference is kind of much. Like here is 50 and here is 42.7. So the person that brought this model to us and is telling us that this model is actually good for the velocity of a falling ball is not a very good model, because just looking at the table, you will know that it's not good. Then when we got the straight line, like this one, the mathematical model we derived in the first class is actually better because the slope is close to 1, but here is like is a little bit far from 1. So this is more closer to 1 than this. Then the intercept, this is more closer to 0 than this. So minus 0.85 is closer to 0 than 5.77. So if you are not, so another measure is we can calculate the standard error of the estimate. So we can calculate the standard error of the estimate using this particular formula. So what we can also do is that we can also calculate this error. So the one that is closest to 0, because we want to drive this error to 0. So the one that is closest to 0 is the better model. Another quantification we can do is the correlation coefficient. So we measure this. So the one that is closest, the model that is closest to 1 is actually the better model. Though I didn't do all of this, but you can also do it to know which model is superior. So given the principles we've learned, we know that this particular model of the velocity of a falling ball is actually better than this particular model that we didn't even know how it came about. Okay, so we're going to make use of Excel to calculate it. Like I said, I generated this table in Excel. So before this lecture is over, we're going to write the computer program that is going to be able to do all of this for us. Okay. Another thing we want to talk about is because the linear regression, we just talked about linear regression, that's fitting a straight line through the data. But how about if you have this set of data points, and obviously if we try to fit a straight line through the data, you know that this is not like correct. because this model is like a curve, and we are trying to fit a straight line through the data, so it's not even appropriate. What is better is using a curve line to fit this particular data point. So we are going to look at how to fit non-linear models or data points that have non-linear relationship. So one way is that before you actually do curve fitting, one thing you have to do is that you have to plot and visually inspect the data to be sure if a linear model applies. Because for this particular question we're given, this blue line is the data points we were given. So the first step we should have done actually is to first of all plot it to see if it's even actually reasonable to fit a straight line through the data. So if we've done that at the first instance, we would have known that, okay, yes, you can fit a linear line or a straight line through the data. Then for the second question also, if we've plotted the points, so this is the blue line, the one given in the blue line. If you've plotted it, you would like have an idea that it is possible to fit a linear line through the data. So so the first step is that you should first of all plot the data points you are given and to see if you can actually fit a linear model through through the data points. And like we just seen in this case, a linear model fit through the data points is not appropriate because it's not going to describe the general trend of the data. So we need a non-linear model. So one of the things we are going to consider is that we are going to use a non-linear model in the next section. But in this section, what we are interested in is that we want to linearize. So given a non-linear relationship between the x variable and the y variable, we want to linearize it. We want to convert it into a linear line, into a straight line, sorry, so that we can fit a straight line through the data. So there are different types of non-linear models that we have. One is the exponential model, and the exponential model is given by this relationship. We have the power model or the power equation. The exponential model as an exponential as a in the equation. Then for the power model, you have this form. So this constant, then x raised to power another constant. Then you have the saturation growth rate. So these are the types of non-linear model we can fit through a non-linear data. So once we've plotted the data points and we know that, okay, this particular data points, we can't use a linear model. So these are the three non-linear model we can fit into through the data point. So what we want to do in this section is that we want to linearize it. So this is the exponential model. When it's linearized, it becomes a straight line. So this is the power equation. When it's linearized, it also becomes a straight line. Then this is the saturation growth rate, non-linear model. And when it's linearized, it becomes a straight line. So what we want to do now is that when we are giving a non-linear, the data points, the relationship between the variables are non-linear, we want to fit a non-linear model. But the strategy we want to employ is that we'll first of all linearize it. So the first non-linear model, which is the exponential model, the way you linearize it is to take the natural logarithm of both sides. So this is the equation here. Is the equation here. Then you take the natural logarithm of both sides as a way of linearizing it. So you take the natural logarithm of this and you take the natural logarithm of this. Because we have a nonlinear model and we want to linearize it. So when you break it down, this particular equation, you arrive at this. So ln alpha plus beta 1 x ln e. So ln e is equal to 1. So you have this linear model. When we started with a non-linear model, but we've been able to linearize it. If you look at this equation, is of the form y is equal to mx plus c, where in place of y, we have ln y. So in place of m, you have beta. Then in place of c, you have ln alpha. So we've been able to, because this is a linear relationship, so this is a non-linear relationship, we've been able to linearize it. So remember that linear models or linear equations are equations that you can express with simply addition and multiplication. So for the second model, which is the power equation, this is the model. So we linearize it by taking the logarithm to base 10 of both sides. So this is the original. So this is the original, sorry, this is the original nonlinear model. This is the original nonlinear model. This is the original nonlinear model. So in order to linearize it, we are going to take the base 10 logarithm of both sides of the equation. So this is a power equation. So taking the logarithm of this, we arrive at this. Then simplifying, the logarithm of this is given by beta 2 log x. So we've been able to linearize it, because if you look at this particular equation, equation 16, is similar to y is equal to mx plus c, where y is given by log y, then m is given by beta 2, then c is given by log alpha. So for the last nonlinear model, you linearize it by taking the inverse of both sides of the equation. And when you take the inverse, you arrive at this. Then the final form is this. Then if you compare it to y is equal to mc, when you compare it with y is equal to mc, in place of y, you have this. Then in place of m, you have this. Then in place of c, you have this. So this is the strategy that will be employed in linearizing nonlinear models. So we'll move to the next example. And the next example says that we should fit the nonlinear model of equation 13 to the data that is given to us. So this is equation 13. So we are asked to fit this particular non-linear model to the data given to us. So this is the model we are to fit into it. So given this particular question, the way we linearized it was to, so when we linearized it, this was the final, when we linearized it, this was the final result we got when we linearized it. So let me just bring it close here. So we are asked to fit a non-linear model, which is given by this. So when we linearize it, we got this. So what you need now is that you have to, because when you compare it with the linear model y is equal to mx plus c, you have, this is your y, then this is your m, then this is your c. So what you need to do now is that you take the log of x and you take the log of y, because now instead of this normal y, we're using log y, and instead of this normal x, we are using log x. So in order to describe it, we actually c plus mx. So instead of the normal y, we're using log y. Instead of the normal x, we're using log x. So the first thing is that you're going to take the log of x, then the log of y. This is the log of x, then this is the log of y. Then remember that we're actually using, we want to get the intercept. So to get the intercept, we need to get the summation of this. We need to get the sum of this, the sum of the y. Then we need to square the x, then get the summation. Then we need to multiply x by y. Then we get the summation. So this is what we've just done. Then when we, so these are the values we arrived at. Then when we put all of these values we've gotten. So this is the sum of log x. This is the sum of log y. This is the sum of log x squared. Then this is the sum of log y squared. So when we do all of this, we put it into this equation, we arrived at the intercept given by this. Then for C, we need to get the mean of the y, then the mean of the x, then this m we got here, we put it here, then we arrive at the intercept. So it turns out that this particular intercept and this particular slope and this particular intercept is the you're going to get a straight line through the data. So let me go back to the table. So this was what so this is the intercept. So here is the intercept, and here is the slope of the line that we got. So using the linearized form. So in order to convert back into the non-linear form, so this is the linearized form, and this is what we got. So this is the intercept, and this is the slope. Using the linear form. So if we are to plot it, so if we are to construct this particular table, so this is using the linear form. So this is our intercept and this is our slope. Then we just put in log x here. So this is log x value to arrive at this particular values. Then for this particular value, we are turning it back into the non-linearized form. So the equation we just derived, this particular equation is the linearized form. So in order to get the non-linearized form, so now the non-linearized form is that when you compare this and this together, so we know that log alpha is given by minus 0.3, then beta is given by 1.75. So in order to get alpha, because once you get the non-linearized form, you just take the antilog of this value. So when we take the antilog, we arrived at 0.5. So beta is still the same thing. We don't need to apply any operation to beta because log alpha is equal to this, then beta is equal to this. So no need of applying any operation to it. So the non-linearized form is given by this equation here. So this is a non-linearized form. So 0.5 x raised to power 1.75, which is given by this. So this is 0.5 x raised to power 1.75. So this is the linearized form. This is the linearized form, and this is not linearized form. So when we plot this value as a function of this value, so the highlighted columns, when you plot it, you are going to arrive at this curve. So this is the straight line, the model we derived when we fit the data. Then these blue points are the data points that were given in the question. So if you look at it, it fits, the data point fits the line perfectly. Then for the non-linearized form, so we plot this as a function of this. And when we plot it, we arrived at this non-linear relationship. So using when you have a non-linear relationship, you can fit a non-linear model, but you first of all have to linearize using the parameters I just described. Then you arrive at the linearized form or the non-linearized form. So the next topic we are going to go into, so this first one is when you have a non-linear relationship, you try to linearize in order to get the non-linear form, then you convert back to the, so in order to get the linear form, then you convert back to the non-linear form. But now we don't want that conversion, we don't want to linearize. So we just want to fit a polynomial. When we started, I talked about linear regression, so fitting a straight line, and polynomial regression, that's fitting a curve. In order to fit a curve, for the straight line, we're using y is equal to mx plus c. But for the polynomial, we are including another term which I've highlighted, m subscript 2 multiplied by s squared. So this is, we are fitting a second order polynomial through the data point. So we want to fit a second order polynomial through the data point. So if we wanted to fit a third order polynomial, this would be the equation. But here is going to be plus, then this is going to be m3, then x raised to power 3. So this is fitting a third order polynomial. But in this, we just consider second order polynomial. Then you can use the same principle to fit a third or fourth order polynomial. So similarly to what we did, we want to minimize the sum of the squared error between the model and the data points we're given. So this is the data points we're given, and this is the model. So we want to minimize the sum of the squared errors. We want to drive this to 0. So we want to drive this summation here to 0. So similar to what we did for linear regression. So the first step is to differentiate this equation with respect to the coefficient. So we differentiate this with respect to the c, which is the slope. Then we differentiate the same equation with respect to, so c is the intercept. So we differentiate this with respect to m, which is the slope. Then we differentiate this with respect to the third coefficient, which is m2. Then we arrive at this. So this is just simple differentiation. Then after that, we are going to equate these equations to 0. We are going to equate all of these equations to 0. Then we're going to expand it out. So this minus 2 terms will disappear because you divide both sides by -2. So they're going to disappear. Then you make this the subject of formula. This is the subject of formula for this equation. Then this is the subject of formula for the third equation. So we arrive at 3 sets of equations. So I want to ask, this particular set of equations, they look familiar. So can somebody tell me what they are? These 3 equations. They look familiar. So how can we solve it? The first question is that, what's the name for this set of equations? Then you should know, because we want to solve for M2, we want to solve for M, and we want to solve for C. So can somebody tell me what are the set of equations and what are the methods we can use? Because we want to solve for M, which is the slope. We want to solve for C, which is the intercept. Then the last coefficient, M2. So that's my question. I need feedback from you guys. So what are these sets of equations and how do we solve it? I'm waiting for an answer. Okay, you can use substitution and elimination method. Okay, all right. Do anybody have any other okay, someone said linear regression. Okay, you probably you don't uh probably you don't understand my question. My question is, we have these sets of equations, these 3 sets of equations, and we want to solve for M1, sorry, M2, want to solve for M, and want to solve for C. So my question is, these 3 sets of equations, what are they actually? Is it familiar? Then how can we solve it? Are there any other, those people that have answered in the chat, I can see your answers. But do any one of you have any other answers? So what are these sets of equations and how can we solve it? Okay, yes. So somebody actually got it correctly. So these sets of equations, that was the topic we just finished last week. So these are linear algebraic equations. So there are sets of 3 simultaneous equations, and we want to solve for M2, we want to solve for M, and we want to solve for C. So we can use different methods. We can use Gaussian elimination and to solve for M2, M, and C. We can use LU decomposition. We can use Jacobi iteration. We can use Gauss-Seidel methods. So those are the methods we can use. Probably I should give you more assignments, because I know if I had given assignments, then you guys would have been fast in giving me the answer. Probably it's because I didn't give any assignments on that last topic. That's why. Okay, so what we want to solve for is, we want to solve for M, because M is common to to the 3 equations. C is common to the 3 equations. So the C I'm highlighting, then M2 is common to the 3 equations. So you can reduce this equation into, let me just write it, AX is equal to B. So, and AX is equal to B. So in matrix form, you have your, because there are three sets of equations. So you have your 3 by 3 matrix, which is your A matrix. Then you have your X matrix. Then you have your B matrix. So in matrix form, this is the representation where the A matrix, let me just write the A matrix here. So then N is here. Then this is the second row. So I'm reducing the sets of equations into solving for linear algebraic equations. So this was what I was actually expecting you guys to actually answer. So this is your A matrix, because this question is solving for the value of M2. So you're solving for M2. So your X is this M, then C. So this is your A matrix. Then your B matrix is this. Then for the second column, then for the last column. So this is, I've just expressed this particular equation. I've expressed it in the form of AX is equal to B. And the form AX is equal to B is just linear algebraic equation, is a set of algebraic equations. So what we need is that we need to solve for X. In our case, X is given by this matrix I highlighted. So now X is equal to A inverse multiplied by B. Sorry, A inverse multiplied by B. So these three sets of equations, they are linear algebraic equations. So you can solve them like this. Then you solve for this. So because this is what we're actually looking for. We are looking for this is the M2, this is M, and this is C. So this is what we are actually looking for. So, and for polynomial regression, the standard error of estimates is given by this. So it's a little different. For linear regression, M is equal to 1. But for polynomial, M is equal to 2. So I'm going to end the meeting now. So join me